So, good evening, everyone. Today is a session on basics of CFD and introduction to XFOIL software by Mr. Jaikumar Loganathan. Mr. Jaikumar Loganathan is a proud alumni of MIT belonging to 49th batch of Aeronautical Engineering. He has done his master's degree in aerospace engineering from Purdue University. At MIT, he was the recipient of the prestigious ARDB scholarship and started his career at DRDL Hyderabad. He joined the CFD group of DRDL and was instrumental in developing indigenous CFD solvers to assist the missile development programs. He joined GE Global at work on projects involving a multitude of technologies like heat transfer prediction in aircraft engines and design of gas turbines and wind turbines. He is currently working for GE Verona, where he is leading a global team on advanced methods and tools development for gas turbine design. Mr. Jaikumar has 15 US patents and 12 conference and journal external publications to his credit. So, while preparing the content for this introduction, I came to know about a very interesting thing. Sir has a wind turbine airfoil family named after him. Beyond his professional achievements, Senior continues to stay connected with his alma mater. Senior is the one coordinating with the other alumnus of the 49th batch to provide students with insightful sessions. I take this opportunity to thank you for providing us students with these engaging sessions. Thank you, sir, and welcome to today's session.
Yeah, thank you for the introduction and good evening, everyone. Just to reiterate, I represent the 49th batch of MIT. This is the second lecture we're having. The first lecture was by Anand. Let me start sharing my screen. And I also see Mutturaj in the meeting. So he is my batchmate. He belongs to the automobile department. And he's an entrepreneur based out of Orissa. Welcome, Mutturaj. Okay, so let me see. Let's see if I can share the dashboard. Can you see my screen? Okay. So let's get started. So this week we are going to talk about basics of CFD, and we are going to start using a software called XFOIL, which is used widely by people working on airfoil design and blade design. So this lecture falls nicely as a next step to what Anand covered in the last lecture. He spoke about the role of simulation in aerospace industry. He mentioned how different simulation framework play a critical role in identifying the system parameters, identifying your mission objectives, and laying out the full framework uh, for the detailed design, right? So CFD comes after you've done your, or after you froze your system parameters, right? So CFD is a tool for doing a detailed design, right? Um, so this is a cartoon which Anand only shared with me, so I find it very interesting, and it shows the reality where people try to get onto the CFD software without properly understanding the math or the fluid mechanics or the numerical methods behind that, right? There is nothing wrong in doing that, but you might get lost or you might lose interest if you're just using the software as a black box, right? So it's essential and it's needed to understand some aspects of math and the fluid mechanics basics behind the CFD, so that you can appreciate it better, and you can be a better practitioner of CFD. Okay, so this is going to be the agenda for today. So we're going to look at what is CFD, and then we're going to look at some of the basic conservation laws and the equation associated with that, mass, momentum, and energy. So they become the core for the CFD, where we'll be solving these equations. And we will see the detailed steps of how to discretize an equation, right? So that is very essential. Like you see the equation in a complicated form, but how you can convert it into a form which the computer can understand, right? That is what we're going to see in the discretization of an equation. And then we're going to discuss about the various steps involved in a CFD simulation. Within that, CFD pre-processing is the first step, right? So today we are going to discuss some details of the CFD pre-processing, uh, usually the meshing strategy, the different types of mesh used, right? So we'll stop the CFD uh, topic there, and then we move on to XFOIL. In the coming lectures, we will discuss about the aspects of solvers, and we will also do a practical session on how to mesh an airfoil, how to solve it in a CFD solver, and how to look at the results and make sense out of it, right? So I would strongly recommend the students to read these books. Like they really helped me to understand the concepts when I was a student. The good thing about these books are like they don't straightly jump to the equation, the complexity of it, right? So it's usually like a storytelling, in a very gradual manner. They introduce the concepts, right? So that if you learn like a story, you tend to remember that for a long time, right? It stays with you. So I strongly recommend in case if you're planning to choose CFD and go deeper, then please try to read some chapters from these books. Okay, I'll go to the next slide. So what is CFD, right? So in a very basic sense, so we are using computers, right, to solve uh, or to understand how fluids move and behave, right? So we might be interested in how the fluids behave over a cylinder or an airfoil or inside a pipe. It could be inside a gas turbine or a wind turbine, right? It could be any application, but basically we want to understand, right, how does it behave when I have some sort of you know uh, pressure which is driving a flow, or it might be coming from some other force, right? So this is a very high level introduction, but we'll go a bit deeper, right? So basically what we try to do is we try to break the domain. So domain is something which is we define around the object of interest, right? It could be a domain around an airfoil or a blade, or it could be a domain inside a pipe, right? So and then we break this domain into smaller parts. We call that mesh. We'll also see why meshing is needed, right, in the later slides. So then we solve the conservation equations. Here it's mentioned only Navier-Stokes, but we also solve the conservation of mass and conservation of energy equations along with the Navier-Stokes equation, right? The Navier-Stokes equation are the momentum equations. And then we try to find what is the variables on the value of variables on these mesh points, right? Or on cell centroids. It could be pressure, temperature, velocity, entropy, etc., right? And then once we solve these equations, we get these variables of interest, and then we plot these variables and see how the flow is looking like. What is the pressure force acting on the airfoil, what is the skin friction force acting on the airfoil, to compute the drag, to compute the lift, right? So that is a typical uh, CFD workflow. Okay. Now, so we will start with the conservation of mass. Um, so I don't know how many students are final year, third year, or second year. Can we have a rough estimate? Like, are most of them third year and final year, or do we have second year students also in the call? Okay. Okay. So some of the concepts that we are going to discuss next might seem a bit complicated, or you may not understand fully. So I apologize for that. But just listen to that, right? I think subsequent semesters you will be introduced to these equations and these concepts. So maybe this lecture will make it a bit more easier for you to understand that, right? And remember one thing that don't get perturbed, or don't be afraid of these equations, right? They look complicated, but if you just go one level deeper, they're very simple, right? It's just that we have to take that one extra step to understand what they really mean, right? And people say that mathematics is nothing but the language of the science, right? If you want to understand science, then the science talks to us using mathematics, right? So here, let's look at the conservation of mass, which it's a very simple concept here, which says that the rate of change of mass inside a volume, it could be any volume, right, is equal to the net mass flow into or out of the surfaces that makes up the volume, right? So it's a very simple thing. You can also correlate this to your day-to-day activities, where you pour some fluid. Like the rate at which the mass increases is directly proportional to the rate at which the flow is coming through the surface, right? So that is what these terms are representing, right? So rho is nothing but the mass per unit volume, and then it's the time rate of change of mass per unit volume, right, which is integrated over the volume, and the mass that is coming in through the surface, right? The ds is the surface here, and you see that there is a um, normal component, right? So any surface we will always consider the normal component multiplied by the velocity. So that is the one which is contributing to the rate at which your mass is changing inside the volume, right? So rho dv is the total mass inside the volume, and then d by dt is the time rate of change of that parameter, and then rho u dot n ds is the mass flow across the surface, right? So you see that velocity. So just keep in mind that u means total velocity. This is a capital U. They usually use U in all the fluid dynamics and most of the aerodynamics books, because we use V for the volume, right? So just to differentiate, the capital U is used for the velocity, right? So the component of velocity in the normal direction multiplied by the density that is coming in through the surface is what is going to contribute to the time rate of change of the mass. So that is what this equation is telling. So let's look from a practical example, right? So imagine that you are filling water in a bucket, right? So the bucket is having walls all around, and it has only one open surface in the top, right? So the rate at which the mass is going to increase inside the bucket depends only on the flow that is coming through this surface, right? So that is what this equation is telling you, right? So you don't have to worry about anything else. If I know exactly how much fluid is going to come, the flow rate to the surface, then I know how much the mass is going to increase inside the bucket, right? This is one scenario. So you imagine this scenario where the mass is coming through this surface. At the same time, there is outflow of mass through many surfaces, right? So you have to consider here, like, there is one surface through which the mass is coming, but there are other surfaces through which the mass is going out, right? So the summation of all these fluxes, right, the one which is coming in, which is going to lead to addition of mass, along with the one which is going out, right? You are going to subtract that. So that will tell you what is the time rate at which my mass is going to increase inside this bucket, right? So that is what this equation is telling us. Okay. I'll take a pause here. Any questions so far? Are you able to follow, or do you want me to repeat any of the uh, terms that we discussed before? And how many of you have already started hearing about Navier-Stokes equation? This is the seventh semester, right? So maybe the final year students would have already learned about it in uh, fluid mechanics, aerodynamics, and a bit of CFD as well, right? Yeah, I think the more maybe they will be studying in a differential form, but yeah, right. So in CFD, since it's a finite volume, we actually deal with integration, and we'll see how to discretize later, right? So this is the conservation of mass. Uh, uh, and then we go to the conservation of momentum, right? So which is nothing but the Newton's law of motion, right? Which is applied for a fluid particle. It says that change of momentum inside a volume, right? Let's consider this volume is equal to the net flow of momentum through the surfaces, right? So momentum, you consider momentum is nothing but your rho into the velocity component, right? If you're considering u momentum, v momentum, and w momentum, here is the total velocities shown here. You will see that this equation can be written for three directions or three velocity components, u, v, and w. This is a capital U. Okay, and then the forces acting on the fluid inside the volume, right? So this term is important. So because for you to change the momentum, there should be a momentum which is coming in, right? Like similar to what we saw in the mass conservation equation. Through the surface, there is some momentum coming in, which is this term, the second term. It is also called the convective term, right? Along with that, there is also forces acting on the fluid, right? So when you consider a fluid, there are three forces that could act. One is the pressure force, then the skin friction or the shear stress force, and the third one is the gravity or any body force, right? So usually, if you're dealing with gas, most of the time the effect of gravity is negligible, so we don't consider gravity. But if you're dealing with a liquid, right, something like a tank or a dam, or if you want to understand the dynamics, then gravity becomes important, right? So the pressure and the shear stress or the skin friction, they kind of become the dominating forces that are acting on a fluid, which results in a change of moment, right? So let's look at the terms in details. So it says that the time rate of change of the momentum, right? You see the rho into u is the momentum, which is over a volume, and the the time rate of this is the surface integral. This is not the time, right? This is the surface integral of the convected momentum, right? The rho u, the previous term we saw only rho is getting convected. Here, the momentum is getting convected. Rho u multiplied by a velocity in the, once again, you have the normal component there over the surface, right? That is the momentum which is coming in from the neighboring cell. That should be equal to the pressure force, once again, normal component to the surface, and the shear stress, once again, normal component to the surface, and then the gravity uh, effect on the fluid particle, right? So if you just go through this definition that is given here, it's just nothing but uh, the Newton's law of motion, right? It says that change of momentum inside a fluid is because of the momentum that is convected through the surfaces, along with the pressure and the shear stress acting on it, right? So the um, imagine, so if you just look at the Navier-Stokes equation, you can say there are like five terms. This is the unsteady term we usually call the unsteady momentum change. This is the convective term, which is non-linear because you have two u's here, it becomes u square when you're trying to solve it. So most of the complexities come from the non-linearity in the convective term. Then the pressure and the shear stress. You will see that later that shear stress is a second derivative, and how to solve that we can see later. Okay. So this is the conservation of momentum, which is based on the Newton's law of uh, you know motion. Then comes the conservation of energy, which is based on the first law of thermodynamics, which says that the energy inside a fluid can change because of the energy which is flowing in or out, or the work done. You can it is very similar to the momentum equation, but here we are dealing with energy, right, which is another conserved variable. From energy we will get the temperature, right, depending upon the nature. Either it could be Cp into T, or uh, Cv into T, depending upon the process. But the form is very same, right? You have energy, there is a flux of energy coming through the surfaces, and then if you look at energy, what are the factors that could impact your energy? One is the heat, right? The heat that which is directly coming in. Previously we saw pressure, so the same equivalent you can consider as heat which is coming in or going out. And then the work done by the shear stress, right? So when you are multiplying the shear stress with a u, it becomes work done, right? So there is a heat work and then the shear stress work. Similarly, the work done by the gravity, when you know multiply gravity by u, it becomes the work done by gravity, right? So the time rate of change of energy in a volume along with the convected energy, right, and the heat coming through the surface, the work done by the shear stress and the work done by the gravity, right? This is the conservation of energy. So we usually include conservation of energy only if there is a thermal aspect going on in the simulation, right? Either you have a heat transfer happening through the walls, or if you have a very high speed flow where um, the fluid is getting heated up behind a shock, right? But for normal conditions like subsonic conditions, we usually don't solve the energy equation because the change in temperature associated with the fluid flow is not that high, and it can be assumed to be constant. Okay. So finally, putting together, these are the five equations we necessarily solve in a CFD solver: conservation of mass or the continuity equation. Then the three momentum equations are given here. So you can see that we are writing in small letter here, which is the U momentum, V momentum, and W momentum. Right? And you see the capital U here, which is the convection part. Right? The U momentum is getting convected through the surface. Right? And this is impacted by your pressure and shear stress. And this is U momentum, so only the X direction shear stress and X direction pressure would impact it. Right? So these are the, you can call it the momentum conservation equation, the Navier-Stokes equation, or the basically these are derived from the Newton's second law. Okay, and then we saw that the energy conservation equation, which is based on the first law of thermodynamics. Okay, so there are some in a practical CFD solver, we also solve some turbulence equations. But those are derived from your momentum equation, right? We will introduce a few turbulent terms here, and then we get two additional equation, and that is what we call the turbulent kinetic energy or the turbulent eddy dissipation rate, or the omega k omega equation or k epsilon equation. But they are derived from your momentum equations. Okay, so keep in mind we usually solve these five conservation equations in a CFD solver, and the momentum equations are called the Navier-Stokes equation. Um, any questions or any clarification is needed? Maybe I didn't go into a lot of details because um, it may not be possible to cover everything. Right? So if you want to go into the details of these equations, how they are derived, how the differential form is derived, you will find those in the books that I mentioned before. Right, the J.D. Anderson book has a very nice derivation. um, and you can actually correlate to, like, uh, why this equation is looking the way it is, right, when you go through those equations. Um, so any questions? I'll take a pause here. If there are any questions, I can answer that. Otherwise, I'll go to the next slide. Okay. Um, I'll go to the next slide. So we will. So now the equations are there, right? I think we know. But how do we solve these equations in a computer, right? What are the steps needed to discretize this equation, right? So there are two types of discretization. One is we discretize the domain, that is called the mesh generation. So then we discretize the equation, right? All the derivatives are converted into simple terms, uh, you know, using the numerical method techniques that we're going to see. Okay, so let's take this mass conservation equation and see how do we discretize it. Okay, so here we are starting with the mass conservation equation. We saw that before. So there is a unsteady term, right? The time rate of change of the density per unit volume, we call that's mass, is directly proportional to, or is nothing but the surface integral of flux coming through the surface, right? So we are going to apply this equation on a 2D grid, right? So a few aspects of the 2D control volume. So focus on the center one, which is shown as P here. So this is a 2D representation. So you have delta x, which shows the one dimension, delta y is the other dimension. So if it is 3D, then you can also imagine it will be like a cuboid, and it will have a delta z, right, which will be normal to the page, right? So we can consider this volume, which has got delta x as one dimension, delta y as one dimension, and you can consider that delta z is equal to 1, right? So if you want to compute the volume of this volume, this will be delta x into delta y into delta z, but z is nothing but 1. So it is nothing but delta x into delta y. That is what you see, that the area of the cell or the volume of the cell, you can say. Okay. And you see some nomenclature here. For this cell, there are certain neighbors, right? You have a neighbor cell in the north, and there's a neighbor cell in the west, east, and south, right? So for this fluid volume or cell, the flux is going to only come through these four surfaces, right? There is no other surfaces which is shared by this cell, right? So only through these four surfaces, the flux is going to come, right? That's what they're saying. Cell faces east, west, north, and south. Okay. Uh, are you guys with me so far about this the 2D mesh that we are discussing? Okay. So now let's see how we can break this surface integral, right? So the surface integral is nothing but you have to integrate over all the surface, right? Since because it is a nice rectangle, right? It becomes a summation. So for me to get uh, rho u dot n into dA on the, let us say the east surface, right? You can see that rho u and area of the east surface is just given here, and you will see that this is positive, and the west surface is given as negative, because if you look at the normal direction, right, the face normal, that is in the opposite direction of x. Okay, that's why this is negative. You will see that for north, it is in the same direction of y, right? So that why this is positive. For south, this is in the opposite direction of y, so that's why this is negative. Okay. So now this rectangular mesh is helping us to convert this integral into a summation. Okay. Excuse me. So you might have studied in numerical methods, right? So if you want to find the area under a curve, right, what do you do, right? You break that curve into Excuse me. So you break the curve into small trapezoids, and then you add the area of the trapezoids, right? So that is what meshing or grid generation is helping us to do. So it is helping us to break an integral or convert an integral into a summation problem. Okay. So if you see here, what is rho u a on the east face is nothing but, so this cell will have some density, right? And that is what we are calling as rho e. And this cell will have some u velocity, we are calling as uy. And what is the area of this face? This face is nothing but delta y into delta z, which is 1, right? So like that, if you just look at, we are getting the value of this integral through these terms. Okay, so now we have converted the surface integral into a summation of fluxes coming through these phases, right? And and the fluxes are coming from the neighboring cells. So this is how we kind of represent the surface integral. We next come to the time derivative term here. So the you see that. So how do you take a derivative, right? It's usually the uh, y2 minus y1 by x2 minus x1 if you're just trying to find the slope of a straight line. Similarly here, so the time derivative means the the value of density at a time n plus 1 minus the value of density at a time n divided by the delta time. Okay, and here the dv is there. Dv is nothing but the volume, which is delta x, delta y, and delta z. And delta z is 1, right? So here we are using a numerical method, which is the first order derivative, right? Um, you might have learned that central differences came forward differences. This is a forward difference method. We are converting the time derivative of density into volume into this term, right? So the density on time n plus 1 minus density at time n by delta t into volume delta x, delta y, delta c. Okay. So finally, when you put together, this is how it comes. And if you just look at this equation, right? So what we are interested in is finding the density in the next time instant. Okay. And we know the value of everything, because whenever you're solving a CFD simulation, you will initialize with some value, right? So all the cells will have the values as an initialization, and then slowly the solution will start evolve from your boundary conditions. Okay, so after I'm initializing, I know rho e because I've initialized. I know ue. So all the terms are known, and this is the only unknown here. I want with all the values that I know here, how do I find the density for the next time instance, right? So you can just go through each cell, right? That's what they do in a CFD solver. They go through cell by cell and then solve for density, solve for u momentum, the v momentum, and the w momentum, and the energy using this discretization scheme. And the momentum discretization will look very similar with some additional terms coming from the pressure and the shear stress. Okay. So this is a very quick and simple introduction. Um, don't worry if you don't understand all of this. Slowly, when you go deeper, like everything will make sense. But the key takeaways are: we solve 5 equations, 1 mass conservation, 3 momentum equations, and 1 energy equation, and then we discretize the domain so that the integrals can become a summation. Right? That is the main reason why we are discretizing the domain. So imagine you have a very complex geometry. By mesh generation, what we are trying to do, we are trying to convert into either a hexahedron like the 3D sense, or in a 2D we may convert into a triangle or quadrilateral, because they become simple shapes on which we can convert an integral into a summation, right? So this conservation equations are valid on each and every mesh points, right? That's why we solve these equations on each mesh points, and slowly the solution will evolve from the boundary conditions. If you don't give boundary conditions, you don't get any solution, right? And for a given boundary condition, the solution is unique. Okay. Um, okay. So I'll take a pause here. I just want to hear from any one of you whether you're able to follow, whether it makes sense, or uh, like whether you already read about this or this is all new to you. Maybe one of you can unmute and comment on that.
The final years know the senior, but the third years will not be aware of this senior.
Okay, okay. Yeah, I think slowly you'll be learning this, but see, try to visualize what's happening, right? Because if you just look at the equation and if you just look at this one, it doesn't really make sense, right? You'll only try to buy hard this and then write it on the exam, right? But try to visualize what's actually happening, right? Why are you, what does the mass conservation mean? What does the momentum conservation mean? And how does it, like, on a given mesh or a grid, how do you discretize that, right? So once you get that basic, it becomes really really kind of cakewalk to look at all the rest of the equations. Okay. So now time check. Oh, okay. I think we're already um, 45 minutes into the call. Um, I don't know how much time you have. Can we extend by 15 minutes? Is that okay, Chilian, or do we have our
Yes, senior, that's not a problem.
Okay, okay. So now let's see what are the steps involved in a typical CFD simulation. Okay. So the first thing is we'll define the problem, right? Am I trying to understand the flow over an airfoil, or do I want to understand pressure drop inside a pipe, or is it a shock structure on a wedge, or a missile, or whatever it is, right? We will try to define that, and what are we looking from that, right? So usually in airfoil, we'll be interested in the forces acting on the airfoil, right? Which will be nothing but the integration of pressure and shear stress. And then we'll resolve that into lift and drag, and from there we get the lift coefficient and the drag coefficient, right? And so what is the geometry, right? Is it an airfoil or a cylinder or a pipe, or is it a wing, or is it a full aircraft, or it's a car, right? So we will define the objectives, and then we'll define the geometry, and then what are the flow conditions, right? Is it what is the Reynolds number? What is the Mach number? Is it a turbulent flow? Is it a laminar flow? Right. So what is the angle at which the flow is coming? So we will, and there will be like if you are at a sea level, the density is different. If you're trying to understand the flow or the forces acting on airplane at a, let us say, at a 10-kilometer altitude, right, which is the cruise altitude for an aircraft, then the flow conditions are very different, right? You have a much lower density, much cooler temperature, etc. Right. So you need to first identify those flow conditions, geometry, and also the objectives why we are doing a CFD simulation. So the second step is the pre-processing, and on that we are going to spend some time today. So we usually, like initially, if you look at the industry, they have a master CAD geometry, right, which is used both for mechanical structural analysis, and the same geometry is used for the CFD analysis also. But a mechanical engineer or a structural engineer who's going to do a FEA analysis, their domain is different, right? They will be looking at the thickness of the geometry. They will look at the structure that makes up that component, right? But for a CFD engineer or a aerodynamicist, the flow path is the one which we are interested in, right? So how do you create that flow path from the bigger geometry is the main step. That is what they're calling as geometry cleanup. And then we mesh it, right? We break that volume, the complex volume, into small, simpler volumes, right? Either it could be a tetrahedron, it could be a hexahedron, it could be a prism, it could be a polyhedra, the latest meshes, right? So that is the mesh generation. And then we define the physical models, right? Are we going to solve turbulence? Is it a laminar flow? Then is it inviscid? Is viscosity playing a role? Is it subsonic? Is it supersonic or transonic? So those kind of uh, physical model selection will happen. Then you set the boundary conditions, right? What is the inlet flow angle? What is my boundary condition of the exit? Is it getting into atmosphere, or is it getting into another a pressure kind of if you look at a combustion chamber, the combustion chamber in a gas turbine, the outlet it sees a turbine, right? So you have to set the boundary conditions appropriately whenever you're trying to simulate a combustion chamber based on your downstream component, right? So that is setting the boundary condition. And then depending on the physics, you might choose the solver, right? If it is a subsonic flow, you choose a different solver. If it is supersonic flow or a compressible flow, and then a different solver is chosen. If you have combustion or reactions happening, then appropriately you will choose the solver. And then solver parameters in terms of what is the upwinding scheme I'm using, what is the numerical scheme, it is first order accurate, second order accurate. So those kind of settings you will do. And if it is an unsteady problem, you will also determine the time step. How what time steps I have to progress my solution. And then you run the simulation. So you monitor convergence. Convergence is nothing but you see what is the error that I'm incurring while solving this conservation equation, right? Initially, you have some boundary conditions and you have initialized, right? Initially, the the mismatch between the conservation equations and your boundary condition will be very high, right? So usually you will see a very high residue, or we'll see like a very high error. And slowly, as you keep progressing with iterations, that error will come down. Okay, and then you post process it. You look at the different parameters, velocity distribution, pressure distribution. Then you integrate the pressure and shear stress to get your forces. And then you will suppose if you have experimental data, you can compare it to the experimental data and see whether it's coming closer, right? Sometimes you may have to repeat these steps because you think that maybe the mesh that I'm created initially is not sufficient to get me the right result, right? So then you may go through this steps again. Or if you are happy with the results that you're seeing, then you will stop there and you will report the conclusions, right? So these are the typical steps involved in a industrial CFD kind of environment. Okay. Any questions so far on the process that is involved? Okay. Now let's discuss about the meshing strategy, right? So there are two meshing strategy. One is top down, and another one is bottoms up. Um, so I don't know how many of you heard about the software ISM CFD. So we are going to look at the software in the next lecture. So the ISM CFD comes under top-down meshing approach, and ANSYS fluent meshing and Gambit, they come under bottoms up. Okay, so if you are an expert user of meshing, it really doesn't matter. But if you um, have some sort of a structured mesh need, then people usually sometimes use top down. But um, you know it's a matter of how convenient you are and how expert you are. People usually tend to use either one of the software for all the problems, right? So they can create structured mesh, unstructured mesh on both the approaches. It's just the way the software works, and you can get the same quality. Sometimes you can get the same end mesh on both these approaches, right? So let's look at a typical scenario. In the bottoms up approach, let us say you want to mesh this cube. You will start with meshing the edges first. You will discretize this edge into smaller elements, and from this edge you will create the surface mesh. Like that, you will mesh the surface, and once you have meshed all the surface, from there you will create the volume mesh. Okay, the internal portion is also meshed and you get the volume mesh. That is the bottoms up approach. The top down approach from the CAD, right? You first create a volume mesh. You see that the volume mesh is encompassing the CAD, and then the second step is a very important step, which is the projection of the overlapping mesh surface or the mesh elements onto the surface of the CAD, right? So this is an important step in the top-down approach. So now what they do is either you are interested in the volume outside this or inside this, right? That you have to decide. So in this case, if let us say I'm interested in the volume inside this CAD, then this mesh, all the mesh that is outside the CAD will be deleted, right? And you get the mesh for this one. Anyway, you already meshed the volume, and you will get the surface mesh as a byproduct of the volume mesh, right? Here in the bottoms up approach, you started with surface mesh and then went to volume mesh. But in a top down approach like ISO, you go from a volume mesh project and then you get the surface mesh. Okay, clear on this? So now another important category is the mesh element type, right? You can have a structured mesh or an unstructured mesh. So the structured mesh, usually the elements will be quad and hexes. And the most important thing is in a structured mesh, the neighbor of any cell is implicitly known, right? Let us say it's like a matrix, right? So let's say I call this cell as I comma j. Then the left neighbor or the west neighbor is I minus 1 comma j, right? And the right neighbor is I plus 1 comma j. The north one will be I comma j plus 1. And the south one will be I comma j minus 1, right? So the neighbors are implicitly known. So you don't have to store them separately, right? But in unstructured mesh, each mesh will have an ID, and for a given element or a given volume, you should explicitly store the neighbors, right? For example, if you look at this triangle, so if this triangle, this one, and this one, right? These are the one which are sharing the faces of the triangle. So they become the neighbors, right? So in unstructured mesh, there is no set format of these neighbors, right? So you have to find out those neighbors and store them explicitly. So that is one. Another thing is it's very difficult sometimes to create a structured mesh for a very complicated geometry, right? It is not impossible, but it takes a lot of time, right? So that's where the unstructured mesh becomes very handy, because the unstructured mesh is very highly automated. It doesn't require a lot of manual intervention. And you will see that when we go through a airfoil CFD simulation, we will create an unstructured mesh using ISO, right? And you will see the process involved. The structured mesh is very manual, and sometimes it takes a lot of time to create. But once you create, there is a lot of benefits to that. We will discuss some of those. Okay. Uh, uh, so the so imagine that you are trying to simulate the flow over an airfoil, right? And you know that the gradients, especially the velocity, will vary a lot normal to the boundary, right? And along the boundary, the variation is less, right? So you can create this very high aspect ratio cells, right? You see that along the x, the distance is very high, but along y, it's very closely packed, right? So you have this liberty to create this kind of meshes, because you have some idea about how the gradient is going to look like on this airfoil, right? So that's where the structured mesh will help you, and you can enormously reduce the mesh count, because higher the mesh count, higher is the time taken to solve that solution, right? So with structured mesh, with this tailored mesh, you can really reduce the mesh count by having this kind of tailoring. Okay. And unstructured mesh, if you have a complicated geometry, so imagine you have a flow path is there and you have an impeller which is rotating, and then the flow from the impeller is going into a convolute or a diverging passage, right? So a very complicated geometry, it's very difficult to get a structured mesh here. It's not impossible, but it will take a lot of time, right? So if you're doing some optimizing the weight blade or something, then you would rather do unstructured mesh, do some design iteration, and on your final geometry you might do a structured mesh, right? So any questions on this, the structured mesh or unstructured mesh? Is it clear? Like each one has its own advantages and disadvantages. Hope you're able to understand the basic differences between these two kind of mesh elements. Okay, so now this is the last slide today we're going to discuss. So once you create a mesh, how do you know whether the mesh is good or not, even before solving it? So there are certain metrics we use. So what I'm showing here is all the metrics that are available in ISM CFD, right? Almost 50 metrics are there, but it's many of them are correlated or connected to each other. So usually we look at these three metrics. Um, Quality is a measure of how that element is deviating from an ideal element. So let us say for a triangle, we consider equilateral triangle as the ideal element. And when you create a unstructured mesh, right, you can have all kind of triangles. Excuse me. And then you will see how much of the is the deviation, right? If the quality value is 0, that means it's almost a straight line, right? It's not a triangle. If the quality is 1, that means it's a very nice equilateral triangle. So determinant tells you the orientation of the mesh element. Sometimes it looks like a triangle, but it may not be oriented correctly, right? The way you orient the nodes, right? So if you have a negative determinant, that means um, the mesh is not right. Similarly, we also look at sometimes the max angle, which is also reflected in quality, right? If you look at these mesh elements, so this is a nice cuboid, but if you look here, it's a very highly skewed, right? So if you look at this angle, it tells you, right, we want the angle between these faces to be 90, but here it's less than 90, right? So you can also look at what is the angle between these faces. So these are some of the metrics that are used to identify or qualify a good mesh even before solving it, right? Um, so this is where I want to stop. Maybe we'll quickly look at XFOIL. So we looked at a lot of things today. Maybe I'll quickly recap what all we looked at. We looked at uh, you know the three conservation laws: the conservation of mass, momentum, and energy, and how all these equations are solved in a CFD solver. Right? These are the 5 conservation laws, and we discretize these equations on a grid, and then we convert this. Excuse me. We convert these integrals into a summation using this grid, and then we kind of find out the unknown, right, which is the parameter the next time instant as a function of all the known elements in the current time instant, right? We looked at the CFD process, then we looked at the meshing strategy, top down, bottoms up. We go from a CAD to edge mesh, surface mesh, and volumetric mesh. It's also called the hierarchical meshing, and this is a top down approach. And then we looked at the 2 different types of mesh elements, right? Structured mesh and unstructured mesh. Okay. Any questions so far? Anything is not clear, or anything we need to go back and discuss again? Okay. Now we'll go to XFOIL. Um, Before that, we may have to quickly look at some of the airfoil metrics. Let me see before that's all be open. Okay, I'll take a quick water break. I'll be back in a minute. Okay. See how many people are on the call. Okay. Let me go to the. Shall we start or?
Yes, senior, we can see.
So a few basic airfoil terminology, just to recap, right? See, chord is a line which connects your leading edge to the trailing edge, right? And then actually a chord is a very important parameter. Uh, so sometimes we use the chord length for computing the Reynolds number, etc. Right? And angle of attack is the angle with which the wind is hitting the chord line, right? That is the angle of attack. Oh. And then we have the thickness. So this is the max thick. Excuse me, I'm getting some off. So this is the max thickness. Um, the location of max thickness is also important. So camber is nothing but the midpoint of the top surface and the bottom surface, right? If you just compute the midpoints and draw a line through that, right? So that is the camber line, and camber is the distance between your chord line and the max distance, right? That is the camber. Okay. Um, and then so lift and drag, you have to be so imagine that, I mean, be clear that lift force is always perpendicular to the flow, right? It's not about how the airfoil is oriented. It's always about with respect to which angle the flow is coming, right? And you take the component of force normal to that to get the lift force. Similarly, drag is parallel and pitching moment is calculated accordingly. Excuse me. You see that, right? So here the airflow is coming in this direction. The lift force is computed normal to the airflow. The drag force is computed perpendicular to the airflow. Okay, keep that in mind. And then you kind of normalize the lift force with your dynamic pressure to get your lift coefficient, drag coefficient, etc. Okay. And before we look at XFOIL, I just want to know how many of you had a chance to install the EXE, or how many of you have the EXE with you? Anybody could? How many of you are like, I'm not able to see the screen, but did you get a chance to download it from that website and have it in your laptop? Let's see whether anybody's raising the hand or not. Julian Hassett, a few others. Okay. 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 I see a few hands. So maybe let me go to the screen here. Okay. So now I'm going to start XFOIL. Right? You just have to. I don't know whether what is the EXE name you have, whether it's XFOIL P3 or XFOIL. Both are the same. So let's say, I think it's usually XFOIL P3. Double click that and it opens the XFOIL window. Okay. It's a very simple menu driven kind of a software. So it works only for airfoil, right? You can't do anything else. And either you can load an airfoil if you have the coordinate file, we'll look at that, or you can create an airfoil here. You can create all the NACA airfoils within XFOIL, right? So once you open XFOIL, all you have to do is give a NACA 0012. So it's a symmetric airfoil, 0 camber, right, and 12% thickness airfoil. Click here. So it has created the airfoil, right, but you're not seeing it. So this airfoil has 140 points in that one, or panel nodes, that is displayed here. So if you just put panel parameter, which is called P par, okay, immediately you can see the airfoil, and you can see the distribution of points, right? Here, if you want to change the number of points on the airfoil, you can change it. So it's asking here, right? What is it you want to change, right? If you want to change the number of panels, let's say I want to change n, okay, I'll give n, it'll, which is 140 now. Let's say we change it to like 240, right? And it's asking you want to change anything else. If you don't want to change anything else, just press enter again. You see that now it has created the airfoil with more points. Okay, so this is a very elementary CFD you can call. This is a panel method. I don't know whether you are studying panel methods in any of the CFD course, but if you take the Navier-Stokes equation and convert it to a potential flow, right, then you get the panel method. Okay, so now we have created the airfoil, right? So now if you want to save the coordinates of the airfoil, all you have to do is you have to give save command followed by name of the file. Let us say NACA, let us say CFD NACA 0012 dot. You can give any extension. It could be txt or dat. You can usually give txt, right? So now in this folder, you see that the file is created, NACA, and you can open it in a notepad or textpad and see the coordinates. So it's that easy to create an airfoil. You can create any NACA airfoil here and write out the coordinates, and then you can take it to Excel. You can plot it also. If you go to Excel, if you plot it, you will see the actual airfoil. Okay, so now you know how to create an NACA airfoil in XFOIL and write it out, write the coordinates out. Okay, so this airfoil is usually, it goes, if you look at the points, right, it will start from the trailing edge of the top surface, right? You see, so this is 0, this is 1, right? If you look here, it starts at 1, which is the trailing edge, and it is positive. That means it is on the top surface, right? Slowly the x is reducing. That means you are going in this direction. And then it comes to the leading edge, and then it comes in this direction. And the last point you see here is once again 1, but negative. Okay. So usually in XFOIL, it creates a blunt trailing edge airfoil. It doesn't create a sharp trailing edge airfoil, which is okay, because most of the practical airfoils has a very small trailing edge thickness. Okay, so you don't have to worry about that. So are you guys following so far? We opened XFOIL, and then we created an NACA airfoil. We changed the number of panels by ppar command, right? Let me go to the window here. Can you see that? So we use the ppar command, and then we change the n to 240, and then we saved that to an airfoil, right? So now I can also load this airfoil. Let us say I open a new window. I close the XFOIL window. So I'm going to open XFOIL again from beginning. Now I can load CFD underscore NACA 0012.txt. right? That is the one which we just created. See, it has 240 points. And if you want to see the airfoil, once again, P bar, right? If you put P bar, you can see the airfoil. Any doubts so far? Are you able to follow what I'm doing in this?
Yes, senior.
Okay. So now the next step is to how to analyze or how to get the CL alpha of this alpha, right? I think many of you would have done that experiment in the wind tunnel, subsonic wind tunnel that we have. You would have taken an airfoil model, kept it there in the wind tunnel, kept it at some angle of attack, started the tunnel, measured the pressure, and then you would have found the CP, integrated the CP to get the lift and everything, right? So that is exactly what we are going to do with this airfoil. Okay. So now we will come out of the P par. We are inside P par and we'll come out this by pressing enter, right? So for you to analyze the airfoil, you have to go to operations. It's called OPER. That's the command. Okay. So you go to OPER and you see once you go to OPER, it's putting a I there, which means it is in the inviscid mode. That means it is not going to consider any friction. Okay. But we want friction to be considered, right? So to change it to a viscous mode, you have to type V first. Okay. The moment you type V, it will ask for the Reynolds number. Okay. So how do you compute Reynolds number? Can anybody tell me the formula of Reynolds number?
Rho V d by mu.
Yeah, rho V d by mu. So rho is the density, V is the characteristic velocity or the free stream velocity. D is the characteristic length, right? For an airfoil, it is the chord length. And mu is the dynamic viscosity, which is usually 1.8 e power minus 6. Okay. So if you look at a typical aircraft airfoil, it operates between 0.1 million to kind of 1 million Reynolds number. So we can give 1 million, right? Which is 1 e power 6. Okay. Now it has set the Reynolds number. Now we have to set the Mach number also. For that, you have to press M. Okay. So this XFOIL can be used only for subsonic flows. So the Mach number cannot exceed 0.3. Okay. Subsonic and incompressible flows. So the Mach number cannot exceed 0.3. So you usually give 0.2 as the Mach number. Okay. So now we have set the Reynolds number. We have set the Mach number. That is all is needed. Now we can look at what is the CLCD it is going to generate for one angle of attack. So I'll put alpha 0. So now it has solved it. And you can see it is giving, it's a symmetric airfoil, right? So at 0 angle of attack, the CL should be 0. That is correct. So it will also recap NACA 0012, Mach number 0.2, Reynolds number 1 million, alpha is 0. For that, the CL is this much. CM, right? Because symmetric airfoil, 0 angle of attack will produce 0 pitching moment. And it has given the total drag. Actually, this drag has two components, the pressure component and the skin friction component. So that is the total drag, and it's giving L by D also, which is the lift to drag ratio or CL by CD. Right? Since CL is 0, the lift to drag ratio is also 0. And N critical. N critical is something which is it represents a wind tunnel parameter. If it is 9, that means you're getting a smooth flow. If you're getting a turbulent flow, then we can change the N critical to other values. Okay. Are you able to follow what I'm doing so far? So then we look at a different angle of attack. Let's say alpha 4 degrees. So you see that it's saying that convergence failed, right? It's not able to converge because usually the default iteration is only 10 iterations, right? So we can change the iteration number by using the command ITER. I'll change it to 100. Okay. So we'll repeat the alpha 4 again. So you can see that it converged nicely, and so what you are seeing is the CP plot for that angle of attack. Okay. So same parameters, NACA, Mach number, Reynolds number. Alpha is 4 now. It's giving a CM. So right at the positive angle of attack, you should get a positive CM. And CM is also there. CD is a total drag, which is a combination of pressure and skin friction. L by D is there, and M20 is 9. So are you guys able to follow now so far? Imagine like how much time it will take in a wind tunnel to measure these parameters. Right? You have to fix the model, run the tunnel, take the pressure reading. Once again, then change the angle of attack of the model and then so this is a very handy tool. Now the beauty of this tool is you can do a sequence of angle of attack, right? So for that, what you have to do is you have to put the command ASEQ, which is nothing but angle of attack sequence, right? Press enter. It will ask what is the starting value. I'm going to start at 0. What is the end value? I'm going to do till 20 degrees. So what is the increment? I'm going to do in increments of 1. Okay. And you do that. You can see here. It has created the alpha, CL, CM, CD. This is the transition location. This we will cover later. Okay. Don't worry about this at this point, which is a turbulent parameter. So we'll discuss about this later. But right now, focus on alpha, CL, CD, CM. Okay. So this is what we will do in a wind tunnel, right? If you want to do this sweep, right, it may take one full day for you. I don't know how many of you already had some experience in taking readings in a wind tunnel. So this tool is very, very handy when you want to do some quick studies, right? So now, but how do I copy this value to a file, right? So what you have to do is you have to, I think this is PACC. Okay. So before, so XFOIL, the way it works is now we have stopped at 20-degree angle of attack, right? Now the solution in the memory of XFOIL is around 20 degrees. So immediately if you run 0 degree, it might fail. So you may have to go in steps. Alpha 10, and then I'll go to alpha 0. Right? So now we are at 0 degree. So before accumulating the polar, you make sure the solver is once run at your starting angle. Then you have to use the command PACC, which is polar accumulation. It will ask for a file name. Okay. So I'll say CFD underscore NACA 0012 dot POL. Usually I use this POL just to differentiate between the coordinate file and the polar file, right? So this is the file name in which all the alpha CL CD CM value will be stored. You will see that. Okay. Usually there is a file called dump file. So what happens is whenever you will see XFOIL is writing so many details on the screen, right? If you want those data also to be stored in a file, this is the dump file. You can give some dump.txt or any file name, right? Or you can also neglect it. It will not write anything. But if you want to just go back and see, some details, people usually look at that and see whether each run has converged or not. Then you can give a dump.txt. Okay. So now it says that you can see that the window polar. Okay. It will say that polar accumulation is enabled. So now you have enabled the polar accumulation. So whatever alpha you run hereafter, that data will be stored in that file. Okay. CFD NACA 001. So let's do the sequence again. ASEQ. Starting value is 0. Ending value is 20. I'm going to do it in increments. So you can do it in increments of 1, or you can do also in increments of 0.5. Right? Or any other increment if you want. you can also give 1.5, right? So now you see that it is creating all those polars, and this is the pressure CP plot which is plotting for each angle of attack, right? So now you see that in the screen you can see it has run till angle of attack 20, CL is given there, CD is given there, right? And here it sees the CDF, right? The screen and CDP. So this total CD is giving the split also. How much is because of spin friction, how much is because of pressure. Okay. So now the pack is still on, right? We have to close that file. So once again, you have to type pack here, polar accumulation. Now it will tell polar accumulation is disabled. Okay. So now we go here. And this is the file we just created. You see here nicely, like, and you can copy this, put it in an Excel sheet. Right. Actually, this is data, text to columns, delete next space, finish. Right. Maybe you should have copied the heading also. That's okay. So this is here. Okay. Let me just copy it fully from the file. I can copy fully. Right. So this is what we got from the XFOIL. So let's quickly plot CL. Let's see how it looks like. Anything? See, this is how the CL. This is alpha is looking. Right. At 0, this is the alpha. This is CL. Similarly, you can plot alpha versus CD or CL versus CD, right? So you see the drag bucket here. Drag is very low and flow is started separating here, right? That's why you see a increase in drag suddenly. So that means flow separation has started, right? And that will coincide with the drop in angle of the CL also. You see that post 15 degrees, the CL is dropping. That means the flow is starting separating. Okay. So you can see like how powerful it is. Right? Within a few minutes, we are able to look at a CL versus CD curve. And you can also bring any airfoil. If you download an airfoil from internet, you can also bring that and analyze that in XFOIL. And you can also do, a lot of interesting stuff. You can change the geometry of the airfoil in XFOIL also. Okay. So I'll take a pause here. Maybe we will stop here. So I want you, whoever is interested, to go back and try some airfoils and analysis, right, using XFOIL. There is a nice user document. All you have to do is go to Google and search, let's see. I'll say XFOIL software, right? So this is from MIT. This is the XFOIL software. Then it's a nice. This is the user document, right? If you go here, so it will tell you how to analyze an airfoil. What are some of the. We saw this below, right? A lot of things are there in this help document. You can do many analysis. We just looked at very basic one today. If you people are interested, we can look at some interesting analysis also later. Okay. So I'll stop here. Hope the session was useful, and I'm hoping that some of you will start using XFOIL even for the final year project, right?